In the last issue of the operating system video series, we talked about the abstracting memory addresses and establish their own address space for each process. One way is to use the base address register and the limit register to delimit the process area. However, this method is no longer used in computers today. So why? For example, a process must be continuous and completely loaded into memory. However, if sometimes the process will expand as the data increases, even exceeding the size of the memory. This is how to do. Not only that, when using SMAP technology, copying the entire process from memory to disk may take a considerable amount of time, and vice versa. So, a better way is to chunk it up and divide it into small units, such as 4 KB in size. They are called pages. Only a part of the page will be in the memory. When the address that the CPU needs to access is not in the page in the memory, the corresponding part can be loaded from the disk. At the same time, when the memory is insufficient, the pages that have not been accessed for a long time can be saved to the disk, and then the part in the memory can be deleted. This practice is called virtual memory. For example, this sentence of assembly refers to copying the value in the register to the memory allocation at the address 1000. The assembly here is not for a specific hardware. It may be reverse copy. In short, 1000 here is a virtual address. After the instruction is passed by the CPU, it is first sent to the address converter, which is called a memory management unit, hereinafter referred to as MMU. After the MMU is responsible for converting the virtual address into a physical address, it accesses the memory through the bus. The content of the bus here is more hardware-oriented, so I won't introduce it here. The memory gets the physical address from the bus. It doesn't know the virtual address. Then, in order for the MMU to implement address translation, it needs a page table to record the mapping relationship between the virtual address and the physical address of page frame, called page table. The virtual address space of this process is 64 KB, while the actual memory is only 32 KB. Therefore, at most only half of the pages will be stored in memory. We call the corresponding frame in the memory called page frame, which is used to load a page. As you can see, there is no order in the mapping of the pages. Now, there is an instruction that needs to access memory address 20500. We need to convert this virtual address into a physical address. First of all, the size of each page here is 4 KB. Therefore, address 20500 is 20 bytes away from the start address of page 5. Here, 20 KB is the starting address of the fifth page, and 20 byte is the offset address within the page. Then, according to the mapping relationship, it is a page frame number 3. Its starting address is 12 KB, which is 12288 bytes. Coupled with the offset address in the page, it is a physical address 12308. If we convert them all into binary, it can be seen that the upper 4 digits are 5 and 3 in decimal, which corresponding to the number of the page respectively, and the number of the page frame. The last 12 digits are the same as 20 in decimal, which represents the offset address in the page. Therefore, the MMU only needs to convert the upper 4 bits, and the offset address remains unchanged, and it becomes the physical address. This is the benefit of using binary. Well, if there is a secondary page number in the middle of the page number, or even more, this is called A multi-level page table. The advantage of multi-level page tables is that only part of the page tables can be stored in memory. This is now generally a 64-bit operating system today. The page table has become very large, so it is particularly important. Next, record the page table of the mapping relationship, each of which is called a page table entry. Among them contains the page frame number. One bit indicates whether the page is in the memory. The protection bit records read, write, and execute permissions. There are also modify bit, exit bit, cache proxy bit, and so on. It will not be expanded here. Then, the page table is usually kept in memory. The converter MMU needs to be read from the memory every time it is converted, which is very slow. Therefore, hardware acceleration is required. That is, the MMU temporarily stores part of the recently used page table entries, which is called Translation Loci Buffer, TLB for short, or associated memory. Well, that's the end of the knowledge of virtual memory. We will meet again next time.